Okay, so I explained the basic idea and the differences between one-tail test and two-tail tests. And let's come back to the numerical example of the Starbucks iced coffee case. So the null hypothesis in that case is 16 or greater, and the alternative, so alternative is important. That's where you reject. Alternative hypothesis is smaller than 16. The mean smaller than 16. And suppose that you randomly sample 100 Starbucks coffees and you obtained a sample average of 15.6 ons and standard deviation of 3. So you find in your sample the amount is slightly smaller, like 0.4 ons lower than it has to be. So, like in this case, with these numbers, I am going to calculate t-statistic and p-value and the critical value using lower tail test. So let's just see what happens, how it goes. So first, the t-statistic, no difference. It's same. So what you observe is 15.6, but what you believe is 16. So the difference is standardized by the sampling distribution standard deviation. So 3 is underlying standard deviation for single coffee, and square root of 100, sample size is 100, and combine all of them. The t-statistic is minus 1.33333, just round up. And then, given this p-value, given this t-statistic, the p-value is probability on the lower side of that. So, minus 1.33, and you calculate a smaller side than that, which is 9.18%. So, probability smaller than this much is 9.18%. So, if you use the p-value approach, this p-value will be compared with the significance level. Significance level 10% will reject this case, because rejected if the p-value is smaller than the significance level. So in this case, p-value is smaller than the significance level if it was 10%. Otherwise, if the significance level was 1% or 5%, then p-value is greater, so you cannot reject the null hypothesis. That's the p-value approach. So as you see, this part and this part are exactly the same as what we did in the previous chapter. But this part is actually easier because you only calculate one side probability, right? This is the only difference. And now t-statistic approach. We calculated the t-statistic is minus 1.33, but its decision rule, the threshold decision rule is different now. So 10%, so we'll go back to here. We are going to use these numbers as the threshold, right? So use these numbers, top 10% value, top 5% value, top 1% value. You can find them from Excel. So top 10% value is 1.28. So that means at 10% significance level, minus 1.28 will be the threshold. So because we are doing lower tail, you have to put minus sign in front of it. So, and you reject if t-stat is smaller than minus 1 point something, like this number. So minus 1.28 is greater than this, so you reject. And at 5%, the threshold is minus 1.64. So like 0 is here, minus 1.64 is like minus 1.64 is here. That means your observation t-statistic is closer to 0 than minus 1.64, so you don't reject. So minus 1.33 falls inside the threshold, and 1% same thing, you don't reject. And as you see, the decision results must be the same. Rejection at 10%, but not at 1 and 5%. Rejection at 10%, but not at 5 and 1%. So, t-stat and p-value approaches are equivalent as they should be. And finally, the critical value approach. There is only one side critical value on the lower side. So critical value will be calculated this way. Again, we use Z alpha, which are these numbers. So top 10%, 5%, 1%. And not the same number as we used in the two-tailed test. Otherwise, the same. mu0, S, skirt N are the same guys. So plug in the numbers. And at 10%, critical value is 15.616. 5% 15.508 and 1% 15.301. So 16 ohms is what you have to be, but you allow certain margin of error. And the margin of error will be more wide as your significance level decreases. So, and what you observe, 15.6 is below this threshold, so you reject the null. However, this observation is above those thresholds, so you don't reject the null hypothesis at 5 and 1%. And again, the rejection decision results are equivalent to the other approaches like p-value, t-stat approaches as they have to be. So as you can see, if you keep in mind when you reject which direction you are rejecting, then the procedure is pretty much the same. You just need to pay like a little bit of attention on these details, whether you use alpha or alpha over 2. So that's pretty much all. Okay, then let's study upper tail test 2 in a similar context. Now, suppose that there is another customer complaining that iced coffee is not cold enough. I don't know if it's true or not, but just suppose that the temperature of an iced coffee must be 40 degrees or lower. I don't know, it may be not true, may not be true, but just suppose. So you are testing, and in this case, it doesn't matter if the temperature is lower than 40 degrees, right? Like 30 degrees, 20 degrees, of course, if it's too cold, actually 20 degrees won't be possible. So, anyhow, it doesn't need to be exactly 40 degrees. Lower than 40 degrees are totally okay. But the problem happens if it's not cold enough. So you observe 100 random coffees, and their average temperature was 40.7 degrees, slightly above the standard. And the standard deviation was 4. Standard deviation across coffees was 4. In this case, what is the p-value? Of course, you have to calculate the t-stat first, and then calculate the p-value. Okay, so if you have not finished, pause. So you observe 40.7 degrees, but you believed 40 degrees. So their difference is 0.7. Your observation is 0.7 degrees above the standard. You standardize it. That's the t-statistic. The difference is standardized by the standard deviation, standard error of the sample distribution. So 4 over square root of 100, which is 1.75. T-statistic is 1.75. So, and in this case, remember, it's upper tail test. You reject if the temperature is too high. So you reject only on the upside, right? Only on the upside. So p-value includes only on the upside. If we calculate probability, normal distribution greater than greater than your t-stat, 1.75. Use Excel to find it. It's 4%, right? The p-value is 4%. Again, what's important here is the direction of this probability. In the normal distribution, 1.75 is here, and you calculate only this side, not the other side. Okay, then now let's calculate the critical value. In the same data, what is the critical value for 5%? Do the algebra, stop the video, do the algebra. Okay, so first I want to say this. When you have one-tailed test and significance level is 5%, you have to use z subscript alpha, which is top 5% value, which is 1.64. If it was two-tailed test, you had to use alpha over 2, which is 1.96, which was 1.96 for two-tailed test. But now it is 1.64 because you put all the probability on one side. And anyhow, the critical value is 40 degrees plus margin of error, where you use these numbers. Easy. So you put margin of error 40 degrees above, like 40 degrees plus 0.656 degree. That's the critical value. And if your observation is higher than this critical value, then you are going to reject. But lower side is not a problem. So, excuse me. Your sample average is 40.7, which is greater than your critical value. So you are going to reject the null hypothesis, as I said, right? It is too hot, not cold enough. I mean, not cold enough. So that's how you calculate that. Okay, what remains is the type 1 probability and type 2 error probability. So, and the idea is the same, just remember now. So we are going to calculate error probabilities in one-tail test, but the mechanism is the same. The machinery goes in the same way. Remember, type 1 error happens when you reject or correct null hypothesis. And type 2 error happens when you don't reject a wrong hypothesis. Just remember that definition. So first, type 1 error probability. Actually, you don't need to remember what is type 1 error probability. Just remember, type 1 error probability always equals the significance level. So significance level at 5%, type 1 error probability is automatically 5%. But if you wanted to calculate the probability, then you need to do it. So you are calculating probability of rejection, which is the sample average greater than the critical value, right? Under the assumption that the true mean is 40 degrees. So your coffee is correctly cold, but your measurement was wrong. So you may see it's not cold enough. That is type 1 error. So this probability will be standardized to this form. And again, we will get 1.64 because this is what we used in the critical value. We are doing the same thing in the other direction. So in the end, we will get 5% because it was from 5%. 5%. Critical value was calculated based on 5%. So we come back to the same point. Okay, type 1 error is actually easy. You don't need any algebra. But let's think about type 2 error probability now. It happens when you don't reject it. So when you don't reject it means, so like from your data, the average temperature is low enough. So you don't reject. However, actually, that was your measurement error. There was a problem in your thermostat. Like so, actually, the Starbucks coffee was not cold enough, but your thermostat measured it too low, something like that. So I will suppose that the truth is 41 degrees. So you have to choose a number, but I will just choose 41. It could be a different number, but then the probability will be different. But let me just use 41 as an example. So when the coffee was actually 41 degrees, then that means the null hypothesis is wrong. So type 2 error probability can be calculated. So your observation, somehow for some reason by random error, your sample average temperature is smaller than, lower than 40.656 degrees, your critical value. So it looks okay, so you don't reject, but that was an error. So to calculate this probability, standardize it, use 41 as the mean, and then we know what are these numbers. In the end, you will get minus 0.86. So probability is 19 point something percent. So nearly 19% is the type 2 error probability. And what you can see from here is because it's one-tail test, there is only one probability, right? There is only one inequality. One side, it happens only on one side. And the power is the other side of the type 2 error probability. So 19 something is the type 2 error probability, then 80 something is the power of the test. Okay? So we have one more example in the next video, and we will use the binary distribution structure again to see how it affects the one-tail test. Okay, see you later. Bye.